Everyone, and welcome to the checkered flag of embedded systems. This is my short video to give you guys a presentation on what I have done for my final this year. So before I get into the specifics, I want to give you guys a general overview of what's going on. So we've got my beautiful project overview slide here. So here's the basic concept. I'm going to attach an assembly to the door that when the door opens, it will send some data, or an accelerometer will collect some data. This accelerometer will use that information to wake up the ESP32, which will then send an HTTP request to if this, then that, which will send a notification to my phone and by extension my watch. This extra arrow here is an SD card. When the ESP comes to life, it will write that information to an SD card if it cannot contact this server out here. So this is the basic kind of project overview. I've built an entryway detection system, and don't worry, you will get to see some very detailed operations of it later. Now, after seeing this diagram, I'm sure you guys think I look like this guy, but don't worry, this will all make sense in just a few moments. Okay, welcome to our product demo. You can see that we've got the black Beats box up on the door there, containing our entryway detection system. I'm going to give the door a quick open here, and we can see that after a few seconds, here on my watch, we've actually got a notification that the door was opened at 9:21 in the morning. After our little product demo, I left the sensor up on my door for about 1 day, and this is the data that was collected to the SD card. So we can see here, this is a simple, tiny little Python Jupyter notebook. We're going to go ahead and read in our data. We're going to apply this modulator function, basically to get everything to be inside of 1 day. We're going to plot a histogram. The bin width here is set to just about 1 hour, and here we get the output. So we can see each one of these columns is the number of times that the door was opened in a particular in 1 hour increments after the board was turned on. All right, guys. The first step that I have to kind of explaining how this works is giving you guys a look at the actual wiring. So we can see inside of our beautiful Beats box here, we've got our ESP32, and we've basically got two things connected. The first is the SD card set up in a SPI configuration with those 4 communication wires there. The second is we actually have this little red chip, which is our accelerometer. You can see there we've got SDA, SCL, and the power and ground wires. So this is wired in a simple I2C configuration. The interesting thing to point out here is that the I1 there, which you can see is on the orange wire, is the interrupt pin. I believe it's GPIO 35, and so that pin will allow us to actually wake up the board from sleep. The only other piece here in the box is our little battery pack so that I was able to get this to run while not being connected. So yeah, there's your wiring overview. Welcome into VS Code. I'm sure you all are very familiar with this at this point. So I wanted to go ahead and do a quick overview just of what my code is actually doing and how all of this stuff works. So before I go ahead and get started, I will say this is built together from a bunch of different examples and a bunch of code that I have already. So there is a lot of code in this file, but a lot of it was copy pasted out of other projects. So starting in here in app main, we're going to set up some I2C stuff, and we're going to go ahead and initialize our sensor, which you can see up here is just a large series of sending a bunch of commands to various registers inside of the accelerometer. So the main takeaway from this is we're changing the sample rate, we're changing the sensitivity, we're setting up some interrupts is basically what this whole block is for. We're telling the sensor to activate its low power mode. The particular accelerometer that I have has a low power mode. And then we're just turning it on, telling it, go ahead and go. Start giving us some interrupts. Okay, back in main. We are done initializing our sensor. We're going to go ahead and do some setup for an SD card. So we've just got some structs and some SPI bus configuration. Down here, we're going to set up some Wi-Fi. There's some interesting stuff that you have to do with this kind of flash init stuff. We're going to go ahead and create some groups for some event tracking for Wi-Fi and whatnot. We're going to go ahead and jump into this function, which has even more boilerplate code that I pulled from the Wi-Fi example. This is all going to go ahead and set up Wi-Fi for us so that we can actually go out and connect to a network. The interesting thing that's worth pointing out here is the actual username and password here are defined in this secrets file, which I will not show, but the actual username and password that are used to connect to Wi-Fi are used there. So jumping back down to the bottom, we can see, let's see here, where do we leave off? This whole block here is all setting up Wi-Fi. Then we're going to go ahead and set up sleep. So basically all I'm doing for sleep is I'm saying, hey, enable an external wake up on GPIO pin 35, and then go ahead and enter sleep. So now our device is all configured. It's all started. We're all rolling. Then we go ahead and enter our main loop, where it will, when it wakes up, it will go ahead and mount the SD card, take a reading, which will be the current timestamp in milliseconds from the time the board came to life. It will close that file, unmount the file system so that we're all in a nice, safe, low power mode for the SD card. So this block is doing all of our SD card stuff. Then we are going to go ahead and start our Wi-Fi. We're going to make that request out to IFTTT. We're going to stop our Wi-Fi, and then we're going to go back to sleep. So there you go. That is all the code that was used to make this stuff work. Okay, hi everybody, and welcome to the lab. You can see that we've got all the necessary essentials here. Got a box full of wires. We've got some incredibly janky leads coming over here, and we've got the iOwn digital multimeter. Okay, so for this, I'm just going to go ahead and turn this guy on so we can go ahead and get some power estimates. So board is all booted up. And currently we are reading about 10 milliamps of current draw while the board is sleeping. Okay, that's what we're drawing at sleep. And we're going to go ahead and shake this over here. So now it is writing to the SD card, doing its Wi-Fi messages and everything. I can see it came through to my watch, and we kind of read, I believe, looks like it's hovering around 40 milliamps. Up as high as, I think I've seen 100 in the past. Yep, so we got an initial spike there of 100. It looks like it, on successive requests, is staying a little bit higher. But looks like it's ranging somewhere in the range of 40 to 100 milliamps while it is in active state. Now that we have our power measurements, it's time to go ahead and do some math, which I'm sure you are all very happy about. So we're going to start by just defining all the numbers that we need to estimate the amount of battery life we're going to get out of this project. So starting with that, we're going to take the measurements that we just took with our amazing setup. We can see that the worst case active current draw is 100 milliamps, and the worst case sleeping current draw is 10 milliamps. Next, we need to estimate the amount of time the device spends awake. So for my use case, I'm estimating that I'll open my door about 30 times every day. And I'm also estimating, just by observing this project a bunch, that it takes about a minute or less for it to send a Wi-Fi message out to my phone. So using those two things, if there's 30 detections a day and each detection puts the device in an active state for a minute, that gives us about 2% of the day awake, which leaves us with 98% of the day left to sleep. The last assumption here is that the 18650 battery has a 2800 milliamp hour available to us. So using that information, we can go ahead and calculate the actual battery life. We do this by saying 2% of the day in an active state times 100 milliamps active current plus 98% of the day times 10 milliamps sleeping current gives us an average current draw, 11.8 milliamps on average. Using this gives us a total battery life when we're sleeping, or with sleeping enabled, of about 237 hours. Without sleep, We will 100% of the time be at the worst case of 100 milliamps, which gives us an average current draw of 100 milliamps. Using this against the 18650, we can estimate about 28 hours only of battery life. So because our device is sleeping, we get a total efficiency increase of a whopping 746%. Thank you guys very much for watching, and I hope you all have a fantastic winter break. Thanks.